Hello, and welcome to Acoustics Derivations. In this video, we'll be talking about the general solution to the wave equation. Now, the wave equation is written here on the screen. It is the speed of sound squared times the second derivative of your acoustic variable with respect to x minus the second derivative of your acoustic variable with respect to t is equal to 0. And we'll derive this in a different video. But now we're going to talk about the general solution to the wave equation. Now, we can formulate the general solution in two different ways. One for initial, which is beneficial to be used with initial value problems, and the second to be used with boundary value problems. So the solution that is better for initial value problems, and this is the more common one you'll see like in a textbook, is a combination of a function with the argument is x minus ct plus a function x plus ct. Now, the boundary value problem looks quite similar, or the solution to the boundary value problem looks quite similar, and you'll see that in just a moment. It's once again a function of f plus g, but the argument is formulated a little bit differently. It's formulated as t minus x over c plus g t plus x over c. And we have a lowercase for the initial value problem and uppercase for the boundary value problem, just kind of for clarity for the reader. Like you'll see in textbooks, there really isn't any significance. It's just kind of to remind us, the arguments inside are different. Why for the initial value problems is it formulated this way? Well, if you think initial value problems, that gives you a condition where time is at 0. So you can easily say that u, and I should have been clear here, both of these u's are a function of x and t, position and time. So that's both of these here. Now, so for initial value problems, you're given a condition at time t equals 0. So this then becomes, at t equals 0, simply u of x and 0 is equal to f of x plus g of x. And that's pretty easy to work with. Similarly, for boundary value problems, we have a temporal condition at a given spatial point. For example, x equals 0. So we have at x equals 0, and you can see then that the solution becomes u0 t is equal to f of t plus g of t. And that's much easier to work with than if we had been up here, it would have been f of minus ct plus g of ct. So it's just more out of convenience than anything. So let's explore these solutions just a little bit, and to show that they are indeed a solution to the wave equation. So I will erase everything but the wave equation here, and we'll explore them just a little bit. So let's suppose we have a function. U is some arbitrary function f. So it could be a sine function, it could be a cosine function, an exponential, even a logarithm. And let's suppose the argument is some multiple of x. plus some multiple of t. So ax plus bt is the argument. So a and b are arbitrary constants. So let's then take the derivative of this function and plug it into the wave equation and see what we get. So we can have the first derivative of u with respect to x by chain rule is going to be a f prime of ax plus bt, where the primes indicate the derivative with respect to the argument. Now we take the second derivative with respect to x, and you pull out another a, so we have a squared f double prime ax plus bt. Now let's take the time derivatives. And the second time derivative. Wonderful. So now what we're going to do is we're going to plug this into the wave equation. So I'll put it down here at the bottom. So we're going to have c squared times a squared f double prime ax plus bt minus b squared f double prime ax plus bt is equal to 0. Well, we can cancel out these terms, and we are left with c squared a squared is equal to b squared, which means b is equal to plus or minus a times c. Okay, lovely. So now, just for convenience, let's let a be equal to 1, just for convenience. It's an arbitrary constant, so why don't we make it easy for ourselves and choose 1? And that gives us that b is equal to plus or minus c. So let me write that up at the top here, because I'm going to need a little bit more space. So I can erase. Oops. Okay. So now we can plug this, the a is 1 and b is equal to plus or minus c, into our solution here. We have that u is equal to f of x plus or minus ct. Okay, that looks a little bit more familiar compared to what I had discussed in the beginning of the video, the general solution. But here we have a plus or a minus CT. So that kind of gives us some intuition, or gives us some thoughts about what is happening here. There seems to be some relation between propagation distance x and time that has progressed t. So then the question is, okay, great. So is it the plus or is it the minus that indicates forward propagation? And I'll give you a second to think on that. So hopefully you took a moment and you thought about that. But so for forward propagation, we use the negative CT rather than the positive. So forward propagation is u of x minus CT. So why is that forward propagation? Well, if we're going to keep the argument x minus ct constant, an increase in time corresponds to an increase in x, i.e., as x increases, time also increases. So why then is the argument constant? Well, each value of the argument defines a phase front of the wave, and that's constant for a lossless case. And so similar to forward propagation, we can see that backward propagation then must correspond to the plus case, because as if you want to keep the argument constant, so you can keep the wavefront constant, then as x increases, time must decrease, but time, you know, unless you know something that I don't, time cannot go backwards. Thus, so time increases, thus the only way that the argument can remain constant is if x decreases, or if you're looking at like a number line, x goes to the left. So this is why we call forward propagation an outgoing wave if you're looking at like a number line and starting at 0. If you're standing at 0, it's moving to the right. That's forward propagation in a 1D frame. Backwards propagation would be going to the left. All right. That concludes this video on the general solution to the wave equation.